said, today I will be talking about understanding the regions of multistationarity in chemical reaction networks with using some symbolic non-negativity certificates of polynomials. So without further ado, let us move on to the subject. First of all, I want to start with a different perspective from polynomial optimization. Even though we are not going to talk about polynomial optimization, I wanted to give this to provide a historical background of how non-negativity was started to become a hot topic. So first of all, the constraint optimization problem is a maximization or minimization problem that is given by where your objective function is a polynomial with n variables, and your feasible region, that is the region defined by your constraint functions, is basically a polynomial again as well. So if you have such a setting, then you basically have a constraint polynomial optimization problem. And to give an example of such a problem, we can consider Maxcut. Maxcut is a famous problem in, like, say, computer science, also in mathematics, in computational mathematics as well, which was known because it was like one of the NP-hard problems that was presented by Karp back in the time. So what does this problem is saying you is that if you have a finite graph G with k vertices and weighted edges, then you define something called cut induced by a subset S of the vertices. So this cut is basically just a subset of edges, so that one of the vertices is in your subset that you chose from the vertices and the other is not. So then basically the weight of this cut, the cut induced by this set of vertices S, is just the sum of the weights that you see in this cut. Then the Maxcut problem is basically asking about finding the maximal weight that you can get in such a way. So to solve this problem, like one of the idea to solve this problem is to formulate this as a polynomial optimization problem over Boolean hypercube. So what do I mean by Boolean hypercube? So all of your variables xi has to be you just set them to be 1 if the vertex that you are basically, like, if all of the xi's corresponding to your vertices in here. Corresponding to your vertex in here, and if your vertex is in S, then xi is 1. If your vertex is not in S, then you put -1. And of course, if you look at the expression over here, this guy is 2 if and only if one of the vertices, like if xi is 1 and the other guy is -1, and it is 0 otherwise. And indeed, if you just take the sum over this constraint functions, then you get the maximum weight of a cut that can be in your graph, basically. So this was just an example of a constraint polynomial optimization problem, and I just wanted to give this to give an idea about, like, to show the importance of this class of problems in the computer science and mathematics. So these kind of problems are important, but as I said, we are not going to be solving CPOPs in this talk. We are mainly going to be interested in the polynomial non-negativity, which is closely related to solving polynomial optimization problems. And also another thing that I want to stress in here is that we are going to be focusing mainly on the global optimization, which is the case where your feasible region is the whole Rn. So here is a definition. So we call a polynomial non-negative if it is evaluated non-negatively everywhere in Rn. Of course, you can give a similar definition in the case of constraint optimization. But as I said, we are not going to be interested in this during this talk. And another thing that I want to mention is that non-negative polynomials of V at most 2D in the n-dimensional space forms a cone, which we denote by P and 2D. So by cone, I literally mean that if you take two polynomials, two non-negative polynomials, you can just add them. It will still be non-negative, and you can also multiply a non-negative polynomial with a non-negative scalar. Then you will still have a non-negative polynomial. So this basically tells you that non-negative polynomials has a form of cone in the n. What is this? This is basically n plus 1 choose d dimensional space. Okay, without further ado, let us see why how this optimization and non-negativity are interchangeable. So essentially, what is going on in here is that instead of asking for the minimum value that a polynomial can take, you can alternatively ask for the maximum scalar value, maximum constant value that you can subtract from your polynomial, so that it is still non-negative. So here is a small illustration of this example. So this is basically the really really silly toy example. X squared plus 2, the function is basically the minimum of this function is at 2. But instead of asking the minimum of this function, you can ask how much I can subtract from this function. So this is the red distance over here, so that you are still non-negative. And this basically, solving these two problems will give you essentially the same result. But what does this give us? So certifying a polynomial, is it easier, or is it or is it harder than like directly optimizing the polynomial? Well, this is not the case. Like it's not easier. Of course, if it was easier, then like CPOPs wouldn't be NP hard. Of course, solving CPOPs in general wouldn't be NP hard. But there are some workarounds that you can take. This is basically something that we call non-negative certificates. What a non-negative certificate is, it's a condition that you can check easily, and it applies for a large class of polynomials, and it implies a non-negativity of this class of polynomials. So, for example, one way to do this is to check if f can be written as sum of squares, and this will directly imply that f is non-negative, of course. And one small remark is that a polynomial in Rx, so this is basically I just wrote x in here, but let me mention, like all the time during this talk, there will be always n entries of this vectorized x over here. So a polynomial in Rx is SOS. Then if and only if it can be written as sum of squares of polynomials. This is just a definition of SOS. But what is more important is that the set of SOS polynomials of degree at most 2D also forms a cone, which we denote by sigma and 2D. And one of the questions that directly comes up to one's mind is that how does the sigma and 2D and p and 2D are related to each other, like whether they are same, or of course one of them is contained in the other for sure. But the main question is to ask in here is that whether they are same, if they are different, how different they are. And the story is that the converse does not hold in general. So this means that this means that these two cones are not equal in general. And in 1888, Hilbert actually gave a characterization of when these two cones are equal. And basically, this theorem is telling you that if the number of variables is 1, or if your maximal degree is 2, or if your variable number is 2 and maximal degree is 4, then these two cones are the same. But if you're outside of these three cases, then this doesn't hold, basically. And it is also, like in here, maybe I should also tell that later on in his famous 1900 speech, Hilbert generalized this result and asked, like as one of his questions, namely his 17th question, he asked whether the same holds for if you instead of taking polynomials, if you take the rational functions. He asked whether this holds for rational functions, and then later on by Artin, this was shown to be hold. But this is just a historical remark. This is not something that we are going to discuss thoroughly in this talk. Okay, we said that certifying the polynomial was an NP hard problem, and it cannot be done just using sum of squares in general. But what else one can do? So here is another classical way to certify non-negativity, namely using AMGM inequality. Let me shortly recall what AMGM inequality was. So AMGM inequality is basically given by this formula over here. What you do is you just first take the arithmetic mean. Okay, you have to carry the n over here, of course, to this guy to be arithmetic mean. This basically tells you that the arithmetic mean of n many numbers is always larger than or equal to the geometric mean of n many numbers. And how one can use this to show that a polynomial expression is non-negative? For example, if you choose your x1 as this term over here, x2 as this term over here, and x3 as this term over here, this is basically the arithmetic mean of three expressions, and this is the geometric mean of these three guys. And if you do the simplifications, then you end up that this expression over here, which is a polynomial, is sum of squares. Is non-negative. I said sum of squares, but actually one can show that this guy, this polynomial, cannot be written as sum of squares at all. I'm not going to discuss this in general, but maybe as a historical remark again, this polynomial is the first concrete example of a polynomial that is non-negative but not sum of squares. And this example was first given by Motzkin in 1967, and it is kind of strange that it took a while for people to come up with a concrete example of non-SOS non-negative polynomials. Okay, so here is an approach that was okay. I told you that one can use AMGM inequality to show that certain polynomials are non-negative, and basically this kind of approach was first studied in detail by Resnick in his 1979 paper, and then this approach basically was generalized to something a bigger class of polynomials called circuit polynomials by Wolff and Ullmann in 2016. And a similar approach was independently developed by Chandrasekaran and Shah using exponential sums. If in the audience, if there are some people who knows exponential sums or who are interested in exponential sums, they can also take a look at the same theory using from this paper. Okay, so let me try to give you the definition of circuit polynomial. So this is indeed a really ugly slide, but let me try to go through this with you. So a circuit polynomial is basically a polynomial with in n dimensions. It's a polynomial with n plus 2 terms. So I mean, by dimension, I mean if you have n many variables, you have n plus 2. So n plus 2 terms are given as this. The first n plus 1 term, the exponents of first n plus 1 term, they have to be a simplex, and the exponent of the last guy has to be in the interior of this simplex, and the coefficients of the first n plus 1 term, they are always strictly positive, and we don't put any restriction on this last coefficient over here. And associated to a circuit polynomial, we have a definition called circuit number, which is just this big multiplication over here. And why this guy is important will be shown in this theorem, but let me try to give you what this expression means over here. So there are some p alpha j's which are coming from these coefficients, and there are some lambda j betas, and these lambda j betas are basically the barycentric coordinates of your exponent point beta with respect to alpha j's, and this is unique since this guy is a simplex. This delta is a simplex. There is a unique barycentric coordinate that you can write, and once you compute this theta p, what you can do with this theta p is that you can check the non-negativity of a circuit polynomial with just making a small symbolic check, which is basically given as like if the absolute value of p beta is less than or equal to theta p in the case of beta is an even point, or in the case of when beta is not an even point, you have to consider this inequality basically. And I'm not going to go into the details of like why this theorem holds, but if you literally just go into this paper, it is not a a big idea on the background. What you do is you literally look at this polynomial and look at this critical point and say that, okay, I mean, you just check its critical points. You see that there is only one, and you show that this in this critical point you are 0, and your polynomial is positive everywhere else. And of course, just with sweeping lots of things under the rug, but this is basically the main idea on the back. And maybe to explain this definition a little bit better, let me give you an example of. We already saw this example, but let's go through it over again. So we said that Motzkin polynomial was one of the polynomials that was shown to be non-negative by, but not sum of squares. But here's a detailed way of seeing seeing why it is non-negative. Like we already solved this with just one application of AMGM, but here is basically another way to interpret this. So let's go through this example slowly. So we say that, okay, let's fix this polynomial, but we don't put any restriction on the coefficient of this guy in the middle yet. But all the guys that are in the vertices are they have positive coefficients. So basically, what you do now to show that, like, for which C this guy is non-negative, what you have to do is you first compute the circuit number of this circuit polynomial. So first you do compute the barycentric coordinates of 2, 2, the point beta, which is 1 divided by 3, 1 divided by 3, 1 divided by 3, and then you just do this big, I mean, not a big but small multiplication over here, which gives you 3. And since this beta is an even point, as you can see over here, like if beta is even, then the condition is telling you that the absolute value of p beta has to be less than or equal to delta p. And this is what we exactly do here. So this guy is non-negative if and only if this holds, basically. And one good thing in here is that, like, no matter what you have in p in the coefficients of this guy, I mean, these can be some sort of parameterized coefficients. Even then, you will have some sort of a symbolic condition over here instead of 3. And here is another example. So this guy over here is not a circuit polynomial directly, but it is a sum of circuit polynomials. So, for example, if you consider this guy G1 and G2, let me show you their Newton polytopes. So this is corresponding to G2. This is corresponding to G1. Both G1 and G2 are circuit polynomials, and one can actually check, just as we did in the previous step, their circuit numbers. And basically, if the circuit numbers are when I add them, if it is larger than the smaller than, if the absolute value is smaller than the coefficient of p beta, which is the case in here, then you see that this guy, the sum of these guys, has to be non-negative. And this is basically this the game is going to be the same. Like, no matter how many points that you have in the interior, you can play the same game to find some sort of a non-negative certificate using these kind of circuits. But of course, for every point, you will get a condition. And in the end, if you have like n many points, you just have to take the intersection of kind of an intersection of these conditions, essentially. Okay, so what does this has to do with chemical reactions and stuff like this? So before going into the details of like how to use this, guys, maybe it makes sense to give a small introduction to chemical reaction networks. And First of all, I mean, we have to get a polynomial out of this whatever the chemical reaction networks is, and my aim for the next 5 to 10 slides will be to try to give you an idea of how we get this polynomial from a chemical. First, what is a chemical reaction network? Second, how do we get a polynomial that to check its non-negativity from a chemical reaction network, and what does this mean? So these are going to be the main topics of the next 5 to 10 slides, basically. So a chemical reaction network, as you might remember from your high school or I don't know, undergraduate times, is just a directed graph in the mathematical sense, where like each vertex of the graph corresponds to a species. Actually, I mean, corresponds to a complex, but it doesn't have to be one species in each complex. I mean, it could be something like x1 plus x2 makes 2x2. But first, let's focus on this easy example. What this reaction network is telling you that there is substance x1 and there is substance x2, and it is x1 is getting changed into x2 with the reaction rate of kappa 1. And this reaction rate of kappa 1 is how do we use this? Is that like what does this mean? It's just a parameter that that regulates how likely your reaction is going to occur, essentially. And using mass action kinetics, we can represent the amounts of I mean not the amounts, but we can represent the change in the amounts of x1 and x2 as follows. So basically what you do for x1 is that you just take the okay, this is just a really silly example. It's not clear in here, but what you do is you just take all the guys in here, take the multiplication of their amounts, and then and multiply it with k1, and you just put whatever like how much x1 is getting produced in there. So I know that this is confusing with this example. So let's go over with a little bit more complicated example. So essentially, in here we again have two species, x1 and x2, and the amount of x1 is changing as follows. So from the first reaction, what you get is you use x1 with the amount of 1. So there is a -1 in the beginning, and the reaction rate is basically given by x1 times kappa 1. And in the second reaction, what is happening is that two x1s are getting produced. So there is a coefficient 2 over here, and the reaction rate is basically given by x2 times x2, because there are two x2s in here, times kappa 2. So this is what we get in here. And from the third reaction, the net change in the x1 is -1, because you use one x1 in the last reaction. And this is why you have -1 over here. And basically the reaction rate is given by x1 times x2 times kappa 3. And if you play the same game if you do the same thing for x2, you get the same thing, but with the minuses. But this was, I mean, this doesn't always have to be like this, of course. This example is a really fine-tuned example. So this is why we have like exactly the negative of this guy over here. But in general, it doesn't have to hold. So okay, so now we somehow write down the production rates or consumption rates of x1 and x2 with just using this kappa 1s and x1, the amounts of xi's. And here is a better way to represent this guy. So instead of writing two equations, you can just present this as one matrix equation. So you just consider this matrix N, which we call as the stoichiometric matrix of this reaction network. And this matrix N, so each column corresponds to a reaction. So this column is telling you that one x1 is getting used and one x2 is getting produced. This is telling you that two x1 is getting produced and two x2 is getting used. And this is basically telling you that one x1 is getting used and one x2 is getting produced. And you write down the vector of reaction rates as follows. And if you take this multiplication, you recover this guy over here. And why do we want to write it like this? Because it is we will see in the next slide basically. So from this equation, we see that where these like the x1 dot and x2 dot can only go into certain directions in the three-dimensional in the two-dimensional space, right? Because like it can only move in the direction that is described by this matrix n. So so basically, what is going on here is that this matrix n is kind of dictating you where, like, given a solution of the system, like given a point in the solution, this n kind of dictates you where the solution can go, and the solution cannot leave this stoichiometric subspace that is generated by this matrix n. And this is essentially what we call as a stoichiometric compatibility class of this guy. So given a initial amount, this can only go into the certain place in the space, and this is the stoichiometric compatibility class that you get from this point. And there is actually another way to interpret this. So if you take a full rank matrix, full rank n minus r by n matrix W, where r is the rank of your first matrix n, and the initial vector species x0, then it holds you just look at this multiplication, and it just spits you out a vector in r n minus r. But then, but if you take any other guy, any other xt in this stoichiometric compatibility class, since like if you plug in this guy, then what you see is that the multiplication of this guy, this new x with the w, is again has to be c. So this means that the first initial vector of species is giving you some sort of a c in r minus r, which one can use to identify the compatibility class associated to this initial species amount. And so here is how it goes on our example. So since this matrix n is rank 1, what you get is W is a rank 1 matrix as well, like 1 by 2 matrix essentially, and this W times R equals C is basically giving you one relation. If W had, I don't know, like n let's say L rows, then you would get L many equations like this, and each one of these equations are called conservation equations, conservation laws or whatever. So the thing that we want to do is to understand the stationarity points of this reaction. Namely, we want to understand the solutions of n times vk x is equal to 0. And more importantly, we are concerned with positive steady states in each stoichiometric compatibility class. So basically, we are trying to understand whether there are like multiple solutions in C, Kappa C, or not. I mean, I didn't define what multistationarity is yet, but this is going to be the main thing. So, okay, let's see what does this mean in our example. So let us rewrite this x dot again, and this basically gives you two equations, which are actually, it is one equation. The other one, this is like just multiplied with -1 essentially. So if you look at the zero locus of this guy, you will get a curve in two-dimensional space, and this curve, maybe we can see over here, this black curve over here. This is basically the stationarity points that you can have, the points of stationarity that you can have from this guy, and this red, blue, and green line is corresponding to your stoichiometric compatibility classes, where C is equal to 1 in the red's case, C is equal to 2 in blue's case, and C is equal to 3 in the green's case. And we see that from this picture, we kind of prove that for this guy, it is actually like your system is actually multi-stationary. Okay, there are like bazillion of stable, like monostationary, bazillion of solutions to nvk x equal to 0 given over here, but in each stoichiometric compatibility class, you have only one stationary point that is given by the intersection of these guys. So we say that a reaction rate constant kappa enables multistationarity if we can find a vector of total amount c such that there are at least two positive steady states. So this means that like, if there is more than one stationarity point in any compatibility class, like at least one, then you have a basically in this case we call that this kappa. I mean the k1s up to k3 in our case enables multistationarity. So but how to one really needs to find a better way to easier way to check this. So to do this, we will refer to a theorem by Conradi, Feliu, Vincheva, and Viu from 2017. So this theorem is basically telling you that given a reaction network that satisfies some technical conditions, I don't want to go into these technical conditions in here because this is not related to what we want to do in this talk in general. If these technical conditions are satisfied, and you are given a stoichiometric matrix n with rank r and corank s, then there exists a computable polynomial px such that if the sign of px is -1 to the s for all positive x, then there is exactly one positive steady state in each class. And if the sign of px is equal to -1 to the s plus 1, so it's if the sign is other ways for some positive x, it doesn't have to be for all. Then there are at least two positive steady states in some compatibility class that we don't necessarily need to know. So how do we get this polynomial? So let's go through this over baby example. So this was the guy that we wanted to compute. I mean, actually the cardinality of this guy. So in order to do this, what we do is we first consider. So this guy is given by two equations, right? So this is the first equation. This has to be equal to 0, and this is the second equation. For a given c, this has to hold. But since we know that this is the steady state, so it's this steady state given by our chemical reaction network, and this is the compatibility class. These two has to be satisfied at the same time. So essentially, you need to get rid of the redundancy in here. So what you do is you just first change the first entry of this guy with the equation that you get from from your conservation laws. So if there were more than one inequality, so what you would do is that you always put W in the row echelon form. So you always have, I don't know, like ones, like you always have like essentially like if this if this was happening in the higher dimensions, so you would have more than one equation here, and for the first non-zero element in each column, you would have changed that row in here. So the first element in here was in the first column, so we just changed the first guy now. I mean, in this case, there was nothing else to do because I mean, this W had only rank 1, so this always has to be in the first guy. But anyway, so from this looking at the solutions of the phi c will essentially give us the guys in C kappa C. This is what I'm trying to say. So from this guy, so in order to check whether there are multiple solutions of this guy, what you do is you look at the Jacobian of this guy and take the determinant of this Jacobian, and you end up with this polynomial over here. But this is not the polynomial that we want to solve yet, because still there are some. Is there a question or no? I guess. So there are still some redundancies that we want to get rid of. So what you do is, so we know that this guy has to be equal to 0, and by solving this, you get a positive parameterization of your points in this C kappa C, actually of your points in here. So this is the parameterization, positive parameterization that you get. Then you plug in this positive parameterization to your determinant, and you end up with a polynomial. So like not necessarily a polynomial. It can be a rational function, but you are interested in the denominator of this guy. So the denominator, the numerator is always positive. This guy's numerator is always positive. It's determinants, and the denominator is given by this expression. And we see that this is always negative. So this means that we are in the case. I will just go up a little bit. We are in the case of so rank was 1. So this is always, so we are in this first case. So this means that this guy always will have 1 positive steady state, no matter which kappas you choose or which C you choose. So from this, we will go a little bit higher now. From this baby example, now we will go to some sort of a higher example. So this example is known as two-side phosphorylation cycle. So what does this cycle do? Maybe you remember from your high school biology lectures. There is a molecule called ATP in our body, which is basically how you regulate your energy in your body. Like ATP is a protein with 3 phosphates attached to it, and whenever you break one phosphate, there is energy coming out, and this is how this is the energy that is used in your body essentially. But this doesn't have to appear on ATP. In general, all of the enzymes, all of the proteins in our body are not all, but most of them are getting phosphorylated and dephosphorylated, and this is a regulatory process that happens in all human bodies in every day, in a daily basis, basically. So essentially, in here, E is our protein that is going to get phosphorylated. S0 is our protein that is going to get phosphorylated. E is the enzyme that is catalyzing this phosphorylation process, and F is the other enzyme that is, so E, maybe I can give the specific name. E is called the kinase enzyme, and F is the phosphatase enzyme. So E binds the phosphate to a certain protein, and basically F detaches this phosphate group from this. So in this chemical reaction network, what we have is we have 9 species now. So it's going to be a 9-dimensional. So we are going to work in the 9-dimensional space, unlike 2 previously. And we have how many? We have 12 many reactions occurring in here. So it means that our phi C that we see over here, that will have 12 many rows. So I'm not going to show you the exact steps that are happening over here because the matrices are huge and it's going to look ugly. But let me directly show you the polynomial that we get from this guy if we apply the same procedure. And here are some like we changed the name of some parameters. I mean, we reparameterize it to make it look a little bit beautiful, because otherwise, if you just use small kappa i's, this looks really long and it's hideous. So we just use something called Michaelis-Menten constants, and this is okay. I'm not an expert in the area, but apparently in the chemical reaction networks theory, whenever there is some sort of a structure like this that you see over here, you can use this Michaelis-Menten constants to instead of like kappa 1, kappa 2, kappa 3, you can just represent them with one big K1. But essentially, after you plug in this Michaelis-Menten constants, what you have is this polynomial, this P polynomial over here. And as you see, I marked some of the, I mean, I marked all of the exponents of this guy. And some of them can be negative, and some of them are positive, and some of them are definitely negative. So this is the situation at the moment. And I will just call these guys that are always appearing as B1, and this guy that is appearing only once as B2 for later use. And we know that from previous results, we have only one steady state when B1 and B2 are positive. Of course, why? Because this means that everything is positive in here, so your P is positive. And by the way, I should say that the rank of this guy, the rank of the matrix that you get from this guy is, sorry, the corank is even. So the signs that we are looking are going to be exact opposite of these. So this means that whenever we have negative guys, when we have negative, this will imply the multistationary. So okay. So we had this polynomial. We want to show that this polynomial is non-negative, or we want to show for which kappa i's and big k's this guy is positive, essentially. So okay, we said that we have only one steady state if these both are positive, and we have multistationarity if B1 is negative. So why this is so? So I already wrote this why this is so over here. So B1 is the coefficient of a vertex of a Newton polynomial. So what does this mean? So okay, that was okay. It doesn't matter. There has to be a picture over here of the Newton polytope of this polynomial. But essentially, like once you draw the shape of this Newton polytope, you see that some of these yellow points are in the vertices. And what happens is that let's go through this over a small example. So this is exactly exactly the same. Okay, like a similar scenario. So you have a polynomial, and in one of the vertices you have basically a negative coefficient. And if you have such a scenario, what you have to do is you just look at the normal cone at this vertex and choose a direction in here. Let's say -3, 2. And you just consider the point, the parameterized point, t to the -3, t to the 2, and you just plug in this plug this point into your polynomial. And what you have in the end is a univariate polynomial whose univariate Laurent polynomial whose leading coefficient is negative. So this means that if you increase t large enough, then you will get a negative valuation of this function of this polynomial. And this is enough for multistationarity. Why? Because sorry, I'm going back. But if this guy is, if this condition is satisfied only for some, then this is enough. So this is why finding just one such a point is enough to show that multistationarity is occurring. So okay, this was the picture that I wanted to. I was referring to, but anyways, it's here. So as I said, if B1k is negative, then you have some sort of a vertex, some sort of a negative vertex, and if you consider the normal cone at this vertex and choose a direction, then you can find a negative evaluation of this polynomial. So the main question that we have now is that what happens if B1 is positive but B2 is negative? So now we have all these yellow points as green, and we have only one negative point. And for this, we use a lemma. We call this the reduction lemma in our work. So what does this theorem? What this lemma is saying you that if you have a multivariate polynomial and consider its Newton polytope NP and take a face of it, and consider the polynomial that is restricted to this face, then this lemma is telling you that for any x that any sign that your restricted polynomial that can take is also can also be taken by your original polynomial, and vice versa. So this is essentially like generalizing what we had for this guy over here. So this is basically now telling you that So it doesn't have to be a vertex. It doesn't have to be a one-dimensional facet now. It tells you that you can play this game no matter, like if you have a red point on a two-dimensional face, just as we have in here, you can just it is just enough to focus on this face, on this two-dimensional facet, basically, or in this case, it's also a face. So this is what we do. So we compute. We just call this hexagonal face as tau, and we just restrict the polynomial to this hexagonal face. Now, if you do this, our polynomial is now somewhat smaller, and now the Newton polytope is two-dimensional, and everything is basically everything except C is green. So now from here, just as we did in our second example, I guess, we will try to find circuits to cover this red point, and this will give us a symbolic certificate of non-negativity. So let's try to give an example. One way to do it is to use A1, A3, and A5. And if you use these guys, then your circuit number is going to be basically 3 times the coefficient of this, and this, and then you take the cube root of this guy. And if the coefficient of if minus coefficient of C is less than or equal to theta, that the number that you calculate over here, then you know that the polynomial that you have is the polynomial that is supported on these 4 points is non-negative, and we know that the rest was already non-negative, so the whole thing is non-negative, and the big P is also non-negative, because looking at this face was already enough. Like if you are non-negative on this hexagonal face, then you are non-negative everywhere. But this is not the only thing that one can do on this circuit that one can write. You can actually you can also choose this circuit given by alpha 2, alpha 4, alpha 6 as well, and this one-dimensional circuit and this one-dimensional circuit. So these are all giving you different certificates, but actually by just adding them, you can you can combine them into one big certificate, and now this is actually a better certificate. Why? Because like the first one was just telling you that you don't see this part. The first coefficient was just telling you this inequality with only red guy. This one was telling you with only with the orange guy. But now if you just combine this means that you push your B2 eta into like as far as you can. I mean, not as far as you can, but you push more than you did with using only one circuit. So if you just write down everything back, in the end, what you get is this symbolic certificate for the non-negativity of this big polynomial. And this is basically a way to give a description of the monostationarity region for two-side phosphorylation. So whenever your kappa or your eta satisfies this equation, eta in here is basically like, okay, I shouldn't go back. Eta in here is basically like the vector that you get from small k's and big k's, which was defined by Michaelis Menten constant. So this is the main argument that we have for monostationarity. And here is one corollary of this thing. So here is the same picture. Here's the same hexagon again, but now with proper numbers and everything. This is the real picture of this hexagonal face. So the thing in here for the two-side phosphorylation is that the polynomial px is non-negative if and only if it is song. In this case, this is something. This doesn't always happen. Like this is a rare case. And basically, why this holds is that this is a theorem that was mentioned by many people. That you can see, like all the references in here. Like this result is basically telling you that, like, if you have a support set where all the points in the boundary have positive coefficients, and you have only one negative point in the interior, such a polynomial is non-negative if and only if it is sunk. And this is exactly what we see in the two-side case. And this is some sort of upshots of this approach here. So what I'm trying to say is that like sunk is enough, and sunk actually, like sunk polynomials exactly describe what we want to see, like the multistationarity region in the two-side case. And essentially, like actually what one can do in here is that like instead of trying to look for the circuits one by one, like you can just try to formulate this as as a one big linear optimization problem, and try to, like, for example, like instead of like, so basically choosing this circuit given by 0, 2, 2, and 4, 1 is essentially choosing like is there a way easier way? Okay, maybe I should directly go into some computations, and it will be a little bit more accessible. So I will stop my screen sharing and change it to some other thing now. I hope you can see. Yes. So okay. So what I want to do is essentially, okay. I should have explained this in the other slide. I'm sorry for the confusion. Sorry, I will reshare my slides. So okay, I hope you can see. Yes. Okay. So what I want to do is to essentially, okay, I will just, so there are 10 green points. Okay, these are red, but these are supposed to be green. So there are 10 green points in here, right? So 3 here, and 4 in here. So I want to write this red point as a linear combination, or as an affine combination of these 10 points. And this is essentially, I will just name all of my points from 1 up to 10, and this circuit over here, for example, will be the point corresponding to in 10-dimensional space, where the first 1, 2, third, 4, 5, and the sixth element, the sixth entry of the vertex is given by 1/3, 1/3, 1/3. So essentially, like all of the circuits, or all of the combinations of the circuits that you can get in here can be represented as one big polytope. So this polytope is what I want to show you. Maybe now I can show you what I want to do in here. So essentially, okay, now you see, I hope. So this is what my inequality is essentially can you see my cursor? I hope you can see my cursor now. So the okay, let me just write the other parts of the code, then I will explain to you. So let me get these inequalities. Yeah. So this basically tells you I just said that, okay, like give me these inequalities, and these inequalities basically telling you that alpha, so -2 is larger than, or so -2 plus lambda 1 times 0, lambda 2 times 4, lambda 3 times blah blah blah, lambda 10 times 2 is larger than or equal to 2, and this guy over here is telling you the minus of this guy. So essentially, these the first and the third inequality is telling you that when you take the affine combination, so linear combinations, or affine is better, affine combination of these 10 points, then you have to get 2 in the first entry. And the second and the fourth inequalities are saying the same thing for the second entry of your point. So they have to be equal to -1. Oops. And this guy over here is telling you that the additions of all lambda i's has to sum up to 1, because this has to be the convex, the red point has to be the convex of these other points. sorry, these two are giving you that they have to be equal to 1, and the other conditions are basically telling you that all of the lambda i's has to be positive. So now with this, what you can do is that you can, I don't know, like compute the dimension of this polytop. Okay, maybe I should have written to print. So we see that it's a 7-dimensional polytop, and you can get, I don't know, like the vertices of this guy. And you see that in vertices, we always have, okay, like how to read the vertices in polymake is that the ones over in here is it's there because it's the homogeneous coordinates, but essentially what you look, when you look at over here, this tells you that the first and the 1, 2, 3, 4, 5, 6, 7, 8 guy. So the first and the 8 entries, when they are 1 over 2, this is basically a point in the vertex of this polytop. Now, if we just shortly go back to our talk, sorry, I can't share my screen. So if we just go back again to our talk, this is basically telling you that 1 and the 8, like, so if you take 1/2 of this guy, you are exactly getting this point, and this is basically one of the vertices in this polytop, in this 7-dimensional polytop. So now the story is what to do for higher dimensional, so higher sides. So once you go into 3-side case, the polytop that you get is combinatorially equivalent, but the hexagonal faces start to change a little bit. Now you have 3 red points in here, and you need to cover these 3 red points. And actually, like, you can do this for each point, and each point gives you a condition in 3-dimensional space for 3-side guy, and each of these inequalities, if you take like each of these inequalities describe a region in the 3-dimensional space, sorry, in the parameter space. And if you take the intersections of these 3 regions, then you get a feasible region where this whole guy is non-negative. And you can play the same game for 5, 6, for 4-side. Now you have 5 guys here. For 5-side, you have, I don't know, like 7 guys in here, and this goes on so forth. But at the moment, there is not a good, interpretation of what happens with the polytops when there are multiple points. But this is something that I am still working on, and that I want to enlighten in the one of my next projects. So essentially, as a concluding remarks, I want to say a few words maybe. So basically what we did in here is that we gave a specific condition, specific symbolic condition for the monostationarity in 2-side phosphorylation cycle. And we said that basically we showed that whenever when we are in this case, when B1 is positive and B2 is negative, then the monostationarity region also has some kappa, some parameters that are satisfying. And also, And also another thing that I want to point out in here is that, as I said, this strategy can be generalized to study the multistationarity in the phosphorylation cycle with a larger number of sites. But what is more important is that a similar approach can be used to answer other problems arising in the chemical reaction networks theory, such as like checking the bistability or checking for Hopf bifurcations. And for example, there are some tests, there are some easier ways to detect these, and the conditions that you see in here are again goes over checking whether some polynomial with the parameters given by some real parameters is non-negative or not. So it is exactly the same story, but we just need to use some other polynomial to check its non-negativity. And this is all I wanted to say. I hope you enjoyed. And yeah.
Thank you very much, Oğuzhan.
And here are some of the
references.
Yeah.
Thank you very much for this very nice talk. Now I stop recording.